Today I come to you from beautiful Calumet, Michigan, the upper part of the Upper Peninsula. Today we'll talk about inverse functions, 6.4. Inverse functions, basically, we're going to start by calling them relations because we're not sure if they're functions yet. But an inverse function interchanges the input and output values of the original relation, and that means the domain and range are also interchanged. We're going to talk about this. The graph of an inverse relation is a reflection of the original graph across the line y equals x, which looks like this through the origin. If both the original relation and its inverse are functions, then you call them inverse functions. Okay, this is the whole reason we learned composition of functions in the last section. Functions f and g are inverses of each other provided that f of g of x equals x and g of f of x equals x. They basically undo each other. So the function g, if it's an inverse, is denoted by this f with a -1 superscript and is read f inverse. How to find? Here's the mechanics of finding an inverse relation. So we take our original relation, we switch the x and the y, so I'll write this as x equals 3y minus 5, and then I solve for y. So let's add 5, 3y equals x plus 5, divide by 3, y equals 1/3 x plus 5/3. So now, if I take my calculator and I graph these, I'm going to graph the original, 3x minus 5. I'm going to graph its inverse, 1 divided by 3x plus 5 divided by 3. And on my graph here, which I'll draw on this chart, on this graph paper, I'm going to put the line y equals x. So here we go. So the original line, right, let's do this. It's going to be tough without a straight edge, bear with me. The original line has a y-intercept of -5, and it's up 3/1. So here's the original function right here. Okay. All right. Now what I want to do is draw the line y equals x, which sits something like this, right? Goes, it's got a slope of 1, and it's through the origin. So truly, if you're reflecting across this point, across this y equals x line, the way you reflect, the mechanics of reflecting is, you come and you say the perpendicular distance, I'm using a point here, I have to go that same perpendicular distance the other way. So there's a point on my inverse. This perpendicular distance, I'm going to go that way. Here, it's the same. Now here, let's see, I'm going to go that way. So my other line should come just like this. And if you look at it, it's actually, look at my graph, you can't see, that's what we have. We have a y-intercept of 5/3, and then we go up 1/3. So it's reflected across this line right here. All right. If I wanted to try another line, for instance, what if I had, first I'll take the line y equals 2x minus 4. Okay, the mechanics of it is I switch the x and the y, and I solve for the new y. So x minus 4 equals 2y, divide by 2. So the inverse function is 1/2 x minus 2. And if I graphed those, this inverse function, which we'll denote as up to the -1 of x, and this one really, so we're talking about function notation, right? If I graph these, and you can try it on your calculator and you'll see what I have. So I'm going to put 2x minus 4, 1/2 x minus 2. I'm going to put that y equals x line again and graph it. So this one has a y-intercept of -4 right here. and up 2 over 1. So this line looks something like this, right? Up 2 over 1. I'm doing it very roughly, obviously. Here's my line, y equals x, like this. It's a diagonal right across that graph paper. Now, if I kind of eyeball the inverse at a few points, that'll be a point on the inverse, that'll be a point, it runs through there, and this has, whoops folks, I had to add 4 here, didn't I? Has a positive 2, and that looks about right. So look at this line, if I'm drawing it correctly, something like this. It's indeed an inverse. Okay, this is just the mechanics and kind of trying to visualize it for you. Now, you can verify the functions are inverses. If you go back to the first slide, we said, if you can prove these two compositions get you back to x, you can verify that things are inverse functions. So let's take this, the thing we did originally. Here's the first function. Here's the inverse I found. So I'm going to say f of f inverse of f. Oops, sorry. Let's go back. So I take f with it. That means I'm going to put as the input this. All right. Which means, remember, this says take the input, multiply it by 3, and subtract 5. So I have 3 times my input, and I'm going to subtract 5. So if I distribute, 3 times 1/3 is x, 3 times 5/3 is plus 5, right? So that's x plus 5 minus 5 equals x. Bam. All right, let's try this one. Now we're going to say the inverse of f of x. So now the input to the inverse will be, whoops, 3x minus 5. The inverse says, take my input, multiply it by 1/3, and add 5/3. All right. So 1/3 times the input plus 5/3. All right, 1/3 times 3x is x, minus 5/3 plus 5/3 equals x. All right, we just verified that those functions are inverses. Now, you can also have inverses of nonlinear functions. Now, what's going to happen here, if you go back here to this, both the original function, which was this, and its inverse are functions. I can drop a vertical line, and it only hits once. So these are inverse functions. But we have to be careful when it comes to nonlinear functions. So let's say I want to see what the inverse of a nonlinear function, let's do a quadratic, x squared. All right, so that's approximately something like this. Well, let's put some numbers in it. 1 is 1, 2 is 4, 1, 4. So it looks like this, right? Okay. If we took this y equals x line, like that. Now let's do this. Y equals x squared. I'm going to solve for y. So x equals the plus and minus square root of y. Now if you look at this right here, folks, this is not a function, is it? For this, let me back up there. I wanted to switch x and y. So x equals y squared. Y equals the square root of x plus and minus. So, note, if I put an input of x into that function, I get 2 y's. So as it is not a function. And notice what happens if I drew this. This inverse function actually looks like this if you graphed it. You would actually have to graph this in your calculator by y equals the positive square root of x, y1, and y2 equals the negative square root of x. So this obviously is not a function. But what I can do is if I took this original function, f of x equals x squared, and I restricted the domain to only non-negative real numbers. That is, x greater than or equal to 0. So I'm going to erase some stuff here. So what happens is, let's put our line of reflection. Here is the original function with its domain restricted, right? It can be 0 and greater. Well, when I do the reflection, or the inverse I should say, and the reflection, now that's a function, right? I don't have this positive and negative well, what I'm going to say is, if the domain of f of x equals x squared is restricted to only non-negative real numbers, then the inverse is a function. Okay, so we're going to talk about how we're going to restrict. Now, we've done the vertical line test to test for functions. We are actually going to use a horizontal line test to see if the inverse of f of x will be a function. We can prove it. So let's say, well, let's try to find the inverse of a cubic function. If I graph this cubic function, I'm going to put it in my calculator and then I'll draw what I find here. Excuse me while I try to put this into my calculator. 2x to the third plus 1. Right, the graph of that, if I give myself some axes, actually looks like this, something on the order of this, so just bear with me. If I try a horizontal line test, notice it only hits that original function once. Therefore, the inverse is also a function. If I took the f of x equals x squared, and I did not restrict its domain, remember that's a parabola, it fails the horizontal line test because the horizontal line hits it in 2 spots. Therefore, its inverse, when I do not restrict the domain, is not a function. Okay? Here is the homework we're going to do. We will talk about this Tuesday when I get back, but go through the book. If you have problems with the homework, look at the number of the example next to that set of problems, and it'll help you walk through it. Okay? They're not that hard. You just have to get the mechanics down and then be able to test if the resulting relation is indeed a function. All right, have a great weekend and a great long break.